deep in the heart of a galaxy 32,000 light-years from Earth. A dying star is tearing itself apart, and in its final breath, it's whispering a secret the universe was never supposed to share. Astronomers watching the collapse expected radiation, dust, decay. What they found instead was something impossible. A new element, one that shouldn't exist, not here, not now, not according to any known law of physics. An element that could rewrite the origin story of the periodic table itself. And the strangest part, this forbidden substance may not come from our universe. At all, what did this star die to reveal? Subscribe if you believe the universe still hides unthinkable secrets, and join us as we follow the final breath of a cosmic giant into a discovery that could fracture the foundations of modern science. It began like any other dying star, quietly, invisibly, and far from the gaze of Earth's restless telescopes, buried deep within the Carina Sagittarius arm of our Milky Way, a place as remote as it is forgotten, the hypergiant known only by its catalogue name, KX-289, began its final act. A stellar colossus, once tens of thousands of times brighter than our sun, now collapsing under the weight of its own gravity. This is how stars end, in fire, in silence, and in light. But this was not that. At the Alma Observatory in Chile, a high-altitude symphony of antennae tuned themselves to a whisper in the dark. Their target, the fading signal of KX-289, which for decades had pulsed steadily in the sub-millimeter range. But on a routine morning in August, something in that rhythm changed. The waveforms coming in didn't match any supernova signature, any known death spiral. Instead, there were interferences, stutters, flares, anomalies so peculiar they were at first dismissed as data corruption. But one astrophysicist refused to let it go. Dr. Marissa Holt, a senior researcher known as much for her precision as her intuition, isolated the raw signals. After cleaning the data, what remained was haunting. A repeating pattern, almost musical in its structure. Frequencies that shouldn't cohere, forming what she described as a voice in the static. It was as if something inside the dying star was trying to say something. She replayed the frequencies over and over again. It felt intentional, she would later say in an interview, like a beacon or a countdown. The team dubbed the anomaly Pulse Delta, and what Pulse Delta revealed next would rattle the core of astrophysical theory. Most dying stars emit predictable spectrohydrogen, helium, trace metals formed from billions of years of fusion. KX-289 was no exception, until the last 17 hours of its visible life. That's when ALMA recorded a spectral signature never seen before in any known celestial body. Not in stars, not in black holes, not in distant quasars or colliding neutron stars. It was a new element, a chemical fingerprint that didn't match anything in the periodic table. At first, the team assumed it was an artifact, maybe a miscalibrated detector or interference from cosmic rays. But it wasn't. Multiple observatories across the globe, including those in Hawaii, Spain, and even Japan's Suisei station, confirmed the anomaly. The spectral lines were real. The element was real. And most disturbingly, it was stable. This shouldn't have been possible. In nuclear chemistry, heavier elements, those beyond uranium, tend to be unstable. They decay within seconds, often fractions of a second, into more recognizable atoms. But the emission line from KX-289 suggested an atom far beyond our known table, superheavy, yet perfectly stable. It wasn't decaying, it was singing. Back in Chile, Dr. Holt stood alone under a windless night sky, staring upward at a fading star. KX-289's light had already dimmed to half its brightness, but the new spectral line, what would later be temporarily named Element Zero, glowed with increasing intensity, as if rising to take the star's place. It was like watching something die, and something else be born, she recalled. But not a child of that star. Something foreign, something it had been hiding. Could a star become a vessel? For centuries, we've believed that stars are forges, factories for elements, creating the building blocks of life through fusion. But what if, instead, some stars are gateways? What if KX-289 didn't create this forbidden element, but delivered it? Within 48 hours of the discovery, labs around the world scrambled to simulate the conditions of the dying star. No model could replicate the formation of such an atom under known physics. Its atomic weight, electron configuration, and radiative behavior didn't follow any known family. We're not just missing a piece of the puzzle, said theoretical physicist Dr. Jonas Mehta. We're playing the wrong game. NASA redirected the James Webb Space Telescope to capture final infrared imaging of KX-289 before it vanished entirely, but something unexpected happened. The star didn't vanish. It hovered in a semi-collapsed state, still pulsing, but no longer fusing. Suspended, as if frozen mid-death. Was it dead, alive, or something in between? KX-289 had not gone quietly into the night. It had paused, delivering a mystery that no one was ready for. In its final moments, it reached across time and space to hand us a question too large for our science, too intimate for our philosophy. When the spectral data from KX-289 was first processed, no one expected a revolution. At first glance, the lines seemed like noise-stray wavelengths dancing outside expected ranges. But as the observatory's machine learning filters ran again and again, those so-called glitches resolved into a strange kind of order. The same anomaly appeared across observatories thousands of miles apart. It was no longer a data error. It was a signal. And that signal carried with it the fingerprints of something impossible. The lines didn't match hydrogen, helium, or any of the 118 known elements catalogued by humankind. Not even the synthetic ones created for split seconds in particle accelerators. This was something wholly other than an atom that, by all accounts, should not exist. The discovery was so destabilizing, the ALMA team released the data under embargo. Fearing premature panic in the scientific community, Dr. Ashok Varela, a theoretical physicist from Caltech, was one of the first external experts brought in to analyze the raw numbers. When he saw the spectral signature, he reportedly sat in stunned silence for nearly 20 minutes. Then, quietly, he said, "This is the edge of the map." The element displayed a suite of baffling behaviors. Its mass was several hundred times heavier than uranium, and yet defying every law of known atomic physics. It was stable. Not just stable, but gravitationally active. Unlike anything previously observed, the atom seemed to exert a microgravity field measurable from the radiation alone. An atom with its own gravity. How normally, gravitational pull is a macroscopic property, the result of enormous quantities of matter. But this was different. Theoretical models began pouring out from labs and universities around the world, each trying to explain how a single atom could hold mass signatures beyond its predicted scale. Some theorized that the atom's nucleus wasn't spherical, but a torus, a ring with mass distributed around an exotic core, something that might tap into zero-point energy fields. Others suggested it was bound together not by the strong nuclear force, but something new. By the end of the week, the scientific community was calling it the impossible element. Unofficially, it was dubbed Element Zero, not for its place on the periodic table, but because it broke the table entirely. And if that wasn't enough, a second discovery followed. When viewed through hyperspectral analysis, the element displayed something never seen in natural or synthetic atoms. Phase. Its spectral lines moved, depending on who was observing and from where. In effect, the atom's radiation seemed to respond to consciousness, or at least to observational perspective. The Copenhagen interpretation of quantum mechanics states that observation influences outcome, but never before had a raw element acted like a quantum variable on a cosmic scale. Some laughed, others panicked, and a few whispered the unthinkable. What if this isn't matter, but message? In a secret briefing to representatives from ESA, NASA, and CERN, Dr. Varela laid out the hypothesis that stunned the room. What if Element Zero wasn't just formed naturally, but was constructed, built atom by atom, engineered in a place where the fundamental forces of our universe no longer apply? A hyperintelligent signature encoded not in binary or language, but in physics itself. This is not a mineral, he said. This is a sentence, and we are just beginning to read it. At the European Southern Observatory in La Silla, Chile, spectrograph teams discovered an even more chilling detail. A smaller star orbiting near KX-289 had also begun emitting faint traces of the same element, almost as if infected. A kind of radiation contagion. If this element could spread, then perhaps the star hadn't produced it at all, but had merely received it. Think about that for a moment. What if KX-289 was not the factory, but the receiver? If so, who or what was the sender? Across research communities, debates erupted. Was this a naturally occurring phenomenon? A new layer of the periodic table revealed only under hypernova conditions? Or was it, as one radical thinker from MIT proposed, a breadcrumb, a seed left behind, waiting for a species capable of seeing it and understanding what it meant? It wouldn't be the first time nature had hidden messages in complexity. DNA, after all, is a four-letter language. Pulsars emit in precise rotations. Even prime numbers have been proposed as universal signposts for intelligence. But an element that was a language older than words, one that didn't care who you were, only that you were ready to listen. The gravitational simulations coming out of Fermilab suggested something even more disturbing. When modeled in virtual environments, Element Zero bent space ever so slightly, not through mass, but through field topology. In simple terms, it changed the shape of space-time around it. Like watching a marble press into rubber, one researcher described, but without ever touching the sheet. It defied logic. It defied known physics, but the data was undeniable. We thought we understood the map of matter. We believed the universe ran on a strict periodic rhythm, that every atom could be charted, named, and eventually controlled. But then a dying star blinked and showed us an element that shouldn't exist. And now, the bigger question hangs in the air like an unsolved riddle. In chemistry, every element has a story, a place of birth etched into the nuclear architecture of its atoms. Hydrogen came from the Big Bang, carbon forged in stellar furnaces, gold born in the collision of neutron stars, each one created through processes we can trace, replicate, and understand. But Element Zero, the mysterious substance revealed in the death throes of KX-289, refuses to tell its origin story. Or worse, it may not have one at all. When a sample's theoretical composition was reconstructed at the Max Planck Institute, it shattered the most fundamental assumption in nucleosynthesis. Its isotopic makeup was too pure, too symmetrical, without the telltale instability found in elements near its hypothetical atomic number. Dr. Liu Cheng, a nuclear chemist who had previously led research into synthetic transuranic elements, examined the ratios and came to a chilling conclusion. This isn't the result of natural fusion. It's as if this element skipped the messy process of being born. In nature, there is chaos before order. Stars explode, particles scatter. Gravity pulls matter into dense cores. Through violence, the universe constructs its elements like a blacksmith hammering metal in fire. But element zero, it's cold, stable, without decay chains, without fusion byproducts, no evidence of neutron capture, supernova shockwaves, or cosmic ray interactions. It exists as if it always had, and always will. It's like finding ice, Cheng explained, that doesn't melt even under fire. Physicists at Lawrence Livermore National Laboratory attempted to simulate the creation of element zero using existing particle collision data. They pushed atoms to their limits, recreating fusion environments millions of times hotter than the sun's core. But no configuration could stabilize above atomic number 126, the so-called island of stability. Beyond that, all known elements break apart in microseconds, yet element zero remained whole. This left scientists with two terrifying possibilities. Either our understanding of chemistry is fatally incomplete, or this element is not of our universe. To dig deeper, Dr. Cheng's team employed femtosecond laser spectroscopy, allowing them to capture atomic reactions at a scale and speed never before attempted. What they found left them speechless. The electrons surrounding the element's hypothetical nucleus didn't behave like particles in shells. Instead, they fluctuated, not orbiting, but phasing in and out of localized space. One intern, fresh from a quantum physics program, described it best. It's like the atom knows it's being watched. If that statement seems bizarre, consider this. In quantum mechanics, particles behave differently depending on whether they are observed. This is the observer effect, a foundational but eerie feature of our universe. But it had never been observed in an element. Not until now. Element zero blurred the line between matter and mystery. Its chemistry didn't just defy models, it inverted them. Attempts to model bonding behavior produced equations with recursive feedback, where the elements seemed to reject covalent relationships entirely. In layman's terms, it doesn't want to bind with anything. Not naturally, not easily. Some compared it to noble gases, which are inert and unreactive. But element zero wasn't passive. It was resistant. It pushed back like a force that refused to play by the same rules. It's the ghost of an element, said Cheng, and it doesn't want company. Yet this resistance wasn't universal. In highly isolated magnetic vacuum chambers, a strange phenomenon occurred. When exposed to extremely low-frequency electromagnetic pulses, the element briefly interacted with a specific isotope of xenon, not bonding, but resonating. It was as if the two materials shared a frequency, a memory. This sent shockwaves. Through the lab, could element zero choose what to interact with? Could it be coded to only activate in specific conditions, like a lock designed for one impossible key? Here's where things turned philosophical. If this material didn't behave like matter, What if it behaved like software? What if it was programmed? We've long searched for evidence of intelligent life in radio waves, in mathematical patterns, in distant megastructures. But what if intelligence wasn't hidden in signals, but in substance? What if the cosmos had been seeded not with messages, but with materials meant to be discovered only when we were ready? If element zero is a kind of cosmic code, then discovering it may be less a scientific victory and more of a test. A gate, a threshold we were never meant to cross until we reached a specific level of understanding. And here's the haunting part. The more scientists studied it, the more it seemed to behave like something alive. Not biologically, but functionally. It adapted, changed frequency patterns under different conditions, refused repetition. At one point, its radiation signature altered slightly when the lab's environmental temperature changed by less than 0.1 degrees Celsius. One technician joked, "It's allergic to predictability." But is it a joke if it's true, as this forbidden chemistry unfolds? The scientific world teeters on a dangerous question. Stars are born, they burn, they die, and in that final collapse, they scatter the ingredients of the universe. It's one of the most well-understood life cycles in astrophysics. But with KX-289, that story took a strange and disquieting turn. Because this star didn't just die, it transformed. And at its heart, something emerged that no model had ever predicted. As observatories focused on the fading star, a curious signal began pulsing from its core. It wasn't electromagnetic radiation, gamma rays, or neutrinos, the usual suspects of stellar death. Instead, it was a repeating harmonic in the deep infrared, forming a distinct pattern with clock-like precision. The source was triangulated to the star's very center, where nuclear fusion had long since ceased. Whatever was emitting this pulse was still alive. NASA and ESA diverted deep space arrays to capture high-resolution scans of KX-289's core remnant, and what they found was staggering. The core hadn't gone supernova. It hadn't become a neutron star. It had crystallized into a rigid, fractal-like lattice of exotic matter, something entirely new, a physical structure built around element zero, suspended in a state that defied heat, gravity, and entropy. It was the shape that shook the scientific community most, unlike the messy chaos typical of collapsing stars. This core showed symmetry, near-perfect geometric alignment on multiple axes, like the recursive growth of snowflakes or the Fibonacci spiral of a nautilus shell. It was a pattern, not an accident, and patterns, as any scientist will tell you, are rarely meaningless. Dr. Kazu, an astrophysicist from Tokyo University, described it as the most ordered system I've ever seen emerge from cosmic violence. To him, the structure inside KX-289 wasn't just stable, it was architected, layered in ways that suggested logic, sequence, design. The structure was named the Calatis, a nod to both the star and the Kelvin-defying temperatures under which it formed. But more than just a physical anomaly, the Calatis seemed to be doing something. It was vibrating, subtly, consistently, at frequencies that didn't align with any internal pressure or thermal expansion. One physicist called it a core hum. Others believed it was far more significant because embedded in those vibrations were micro-variations, too regular to be noise, too patterned to be coincidence. A mathematical analysis revealed a string of prime intervals encoded into the pulse rate. Prime numbers, the universal constant, immune to language, culture, or biology. This was no longer just a discovery, it was a communication, But from whom? And why embed such a message in the death of a star? Some theorists proposed a radical idea. What if certain stars are chosen? What if they serve as quantum substrates, hosts for information structures far more advanced than anything we've conceived? Much like DNA encodes instructions for life, the Calatis might be a kind of stellar hard drive, one activated only under precise cosmological conditions. And if that were true, then the timing of its collapse was no accident. Theoretical models suggested that element zero would remain dormant unless exposed to a very specific frequency of gravitational compression, the kind that only occurs in red hypergents at the exact moment before stellar failure. Any deviation and the structure wouldn't form. This wasn't chemistry, it was choreography. A cosmic ballet measured in microseconds and microns. And we just happened to be watching at the exact moment the curtain rose. But this raises an unnerving question. Why now? Stars die every day. Supernovae light up the universe like time bombs on a schedule. But KX-289 had waited. It hovered at the edge of collapse longer than any recorded hypergent. Spectral analysis of surrounding space dust suggested it should have exploded over 200,000 years ago. Yet it didn't. Something had stalled the inevitable. Some hypothesized that the presence of element zero stabilized the collapse. Others argued that we were the missing piece, that the event was somehow waiting to be seen, observed, understood, like a cosmic trigger dependent not on matter, but on consciousness. It's easy to dismiss such ideas as speculative fantasy, but quantum physics is already full of such eerie implications that particles behave differently when measured. That reality is shaped by the act of noticing. So what if, on the grandest possible scale, the universe had built something to be noticed? One chilling analogy gained traction in research circles: the Rosetta Star. Just as the Rosetta Stone helped us decode the language of ancient Egypt, KX-289 might be the key to decoding the cosmic language of matter, a message not written in glyphs or sounds, but in the structure of atoms, the geometry of dying cores. If this was true, then KX-289 wasn't just ending, it was evolving, becoming something else. Something not bound by fusion or collapse, a new kind of celestial being, not a star, not a remnant, but a kind of data crystal, storing information, awaiting retrieval. For all our progress, for all the equations etched on chalkboards, and particles captured in colossal rings of steel, there remains one haunting truth in physics. We don't know what we don't know. And when element zero emerged from the collapse of KX-289, it exposed a blind spot so vast, so fundamental, it threatened to unmake the Standard Model itself. It started in Geneva, at CERN, inside the whispering hum of the Large Hadron Collider. Following the spectral anomaly from KX-289, scientists fed the properties of element zero into their quantum chromodynamics simulations. The results were ... incoherent. Simulations crashed. Particle interactions folded in on themselves, like Mobius loops of code that never completed. Dr. Natalia Roseb, one of the LHC's lead particle theorists, was the first to notice something strange, not in the data, but in its absence. The numbers weren't just off, she said. They were blind to something, like a camera trying to capture a ghost. The simulations acted as if some key interaction, some crucial rule of nature, had been omitted from our physics entirely. That rule, it turned out, wasn't just missing, it had never been written down. In modern physics, every particle is accounted for by specific forces. Quarks bind with gluons, Electrons respond to electromagnetism. Even dark matter, though unseen, fits into certain hypothetical frameworks. But element zero didn't respond to any of it. Its theoretical nucleus rejected all familiar constraints. It didn't bind by the strong force. It didn't decay via the weak. And most disturbingly, it didn't seem to emerge from any quantum field we could identify. It was like a word that didn't belong to any known language, so the team created new simulations, hundreds of thousands of them, modeling interactions outside our current frameworks. Exotic symmetry groups, higher dimensional topologies. They pushed the LHC to process alternative physics. And finally, one set of parameters produced coherence. But the model was chilling. It predicted the stability of element zero only within the event horizon of a black hole. Let that sink in. According to this new model, element zero could only exist in regions of spacetime where gravity breaks the fabric of the universe, where time slows to a crawl, space folds inward, and even light cannot escape. And yet, KX-289 was no black hole. It was dying, yes. Strange, yes. But still visible, still real. How then was this forbidden element existing outside the very place it was born to reside? One theory began to rise, whispered in private conferences, debated behind closed doors. Perhaps KX-289 had hosted something like a black hole, not a singularity, but a near singular, a quantum object right on the edge of spacetime's breaking point, a state some physicists now call a quantum blind spot. This blind spot isn't empty. It's dense, not with matter, but with possibility. A place where the probabilities of quantum states don't collapse into a single reality, but remain suspended, floating, undecided. Element zero may have emerged from such a place, and if that's true, then the implications are enormous. We may have just glimpsed another layer of the universe, one not governed by the tidy forces we've studied for a century, but by forces that haven't yet been named. A hidden operating system beneath the visible cosmos, something deeper than space, more ancient than time. For Dr. Rusev, it changed everything. It's like we've been playing chess, she said, and just discovered the board itself is moving. More anomalies began to emerge. Detectors at Fermilab recorded temporal shifts during high-energy experiments involving simulated element zero conditions. Clocks desynchronized by nanoseconds, insignificant in human terms, but catastrophic in physics. One researcher reported seeing particle paths split briefly and then recombine. It was like watching two versions of reality trying to decide which one would win. Theorists began to revisit discarded ideas, supersymmetry, loop quantum gravity, even aspects of string theory long thought to be mathematical dead ends. Suddenly, everything was back on the table, because now we had something new, something real, something unexplainable. And here lies the philosophical fracture. We always assumed that matter was the final answer, that if we could break it down far enough, reduce it to its smallest parts, we'd find truth. But what if truth doesn't sit at the bottom of reality? What if it lurks in the gaps between our understanding, in the blind spots where logic fails and paradox begins? Element zero may not just be matter from a dying star. It may be a question carved into the universe itself, a question that can only be asked when the right observer, under the right conditions, becomes ready to hear it. If this quantum blind spot exists, how many others are out there? Deep beneath the Jura Mountains, inside the labyrinthine tunnels of CERN, a silence hummed louder than any machine. In the shadows of the world's most powerful particle accelerator, a mystery had begun to take form, not from smashing atoms, but from what lingered after the collision. Something new, something invisible, something that refused to behave. As researchers pushed their simulations based on Element Zero's quantum blind spot, they initiated a controlled experiment to probe deeper into its theoretical properties. The setup was extreme ultra-cold vacuum, chambers, high-energy collisions, and detectors tuned to sensitivity levels that bordered on quantum noise. Most expected failure, but what they saw was nothing, and that was the problem. In frame after frame, a clear void appeared in the data, a null space, as one technician called it, where energy should have been accounted for. The results didn't show particles. They showed holes, gaps in causality, a silent, recurring anomaly, as though a ghost had passed through the detectors and left behind a fingerprint in reverse. Eventually, they gave it a name, the phantom particle. It had no mass, no charge. It didn't scatter light, bend magnetic fields, or decay into anything known, and yet its presence was undeniable. Whatever it was, it interacted, not like ordinary matter, but like a trick of the universe trying to hide something. In plain sight at first, skeptics assumed it was a calculation error, a misread quirk of background noise. But the anomaly held, consistent, measurable, predictable. Its signal occurred only when certain spin states of Element Zero were simulated, and not just in one lab. Independent experiments from the SLAC National Accelerator Laboratory in California and Riken in Japan reported the same silent signature. It was real, but what was it? Dr. Ingrid Knorr, a quantum field specialist from Sweden, took a radical stance. She proposed that the phantom particle wasn't a particle at all, but a transition event. Not something in our universe, but something leaving it. It's a ripple at the edge of dimensional stability, she explained. We're not detecting the thing, we're detecting the shadow it leaves behind. Her paper ignited furious debate. Could a particle exist in a higher dimensional state and momentarily phase through our own? And if so, what governed its motion? Was it random, purposeful, or was it drawn to something? The phantom particle had one more chilling behavior. It tunneled. During collider experiments, it seemed to appear on both sides of solid-state barriers. Quantum tunneling, yes, but on a macro scale never seen before. This wasn't just probability leaking through reality, it was intent. The mathematics defied standard quantum models. Theoretical reconstruction suggested that the particle's waveform had non-local coherence, meaning it could maintain simultaneous phase states across vast spatial distances. In simple terms, it was everywhere and nowhere until it was observed. And even then, it refused to collapse completely. The act of measurement didn't just change it, it irritated it. Technicians began noticing a strange phenomenon. During certain runs of the simulation, equipment behaved erratically. Monitors would flicker, clocks would lose sync, ionization meters would spike, even when no known radiation was present. Most dismissed it as electromagnetic interference, until it happened to a person. During one late-night run, a researcher monitoring the phantom particle simulation reportedly experienced a powerful auditory hallucination, a low hum, like metal vibrating beneath the floor. When she turned her head, she saw a shadow moving across the chamber wall, but there was no one there. Her brain scans, taken hours later, showed signs of transient neural excitation in the temporal lobe, the region associated with language. memory, and perception of time. What was the phantom particle doing to human minds? Was it dangerous? Or was it interactive? The possibility horrified some and fascinated others. A few compared it to a kind of subatomic message, not in words, but in disruption. If you wanted to get the attention of a species conditioned to overlook the fabric of reality, how would you do it? You wouldn't shout. You'd whisper where the silence is loudest, and the timing couldn't be ignored. The phantom particle was only observable when element zero simulations were active. Without it, the particles simply didn't show up. It was like a key turning a lock, one part triggering the appearance of the other dot. So, what were we unlocking? A physicist from MIT posed the most chilling hypothesis yet. What if the phantom particle is a relic? Not a particle created by the death of KX289, but something preserved within it. Older than the star, older than our galaxy. Preserved inside element zero, like an interdimensional seed, dormant until conditions allowed it to slip through. The cracks in reality, and if this is true, then we must ask, where did it come from? Because particles don't exist in isolation. They have origins, histories, forces that shape them. And if this one tunneled in, something else might follow. For over half a century, physics has quietly harbored one of the greatest existential riddles in science, a cosmic imbalance that should have erased us from existence before we ever began. According to the standard model, the Big Bang should have created equal parts matter and antimatter. And when matter meets antimatter, they annihilate perfectly, violently, leaving behind nothing but energy. The math is cold and unforgiving. We should not be here. The universe should be empty, but it's not. Somehow, against every law of balance and symmetry, matter won, and no one knows why. Until now, the discovery of element zero and its companion, the phantom particle, forced physicists to reconsider the foundational question. Why does matter exist at all? At the University of Cambridge, a group of particle theorists, led by Dr. Camille Serrano, began running simulations, feeding element zeros, exotic quantum behavior into barogenesis models. The process believed to have created matter in the early universe. What they found was unprecedented. Element zero, when modeled under early universe conditions, didn't behave like normal matter. It refused to annihilate with its antimatter twin. The simulations showed a slight but persistent asymmetry, a kind of quantum preference. Over millions of cycles, this tiny bias allowed just enough matter to survive, to escape total cancellation. This wasn't just theoretical, it was predictive. Element zero offered a mechanism, a reason, a missing piece in the puzzle of cosmic origins. Serrano's team dubbed it the matter skew principle, and if proven, it would finally explain why anything, from atoms to galaxies to thoughts, could exist in the first place. But this created an even more unnerving implication. If element zero carries the signature of this ancient bias, then it may have been present at the beginning of time. Or worse, it may have preceded it. That idea shook the cosmological community to its core. Dr. Hassan El-Rami, a theoretical cosmologist from Princeton, posed a terrifying possibility. If this element existed before the Big Bang, then our universe may not be the first. It might just be the latest iteration. This is not a new idea. The concept of cyclical universes, births and deaths stretched across eons, has floated on the fringe of physics for decades. But now, for the first time, there was a physical object pointing toward it, a chemical fossil, a piece of prehistory. embedded in the fabric of a dying star, and perhaps left there on purpose at the SETI Institute, normally focused on radio signals from distant stars. Interest surged around element zero. If an intelligent civilization wanted to send a message that could survive heat, gravity, and the death of stars, they wouldn't use metal plates or radio beams. They would use matter itself, designed to endure across cosmic cycles, reappearing only when the physics of a future universe allowed it. In this context, KX-289 may not have discovered element zero. It may have been chosen to deliver it. This reframed the nature of the dying star entirely. Perhaps its collapse wasn't random. Perhaps KX-289 was acting as a kind of cosmic courier, a vault designed to crack open under very specific conditions, ones that happened to align with the tools of modern human science. The timing was uncanny. The geometry of the core, the behavior of the particle, the impossible symmetry of it all. We've long assumed that the universe is indifferent, that its elegance is accidental. But what if we've mistaken design for coincidence? What if we've mistaken a message for mere matter? In a darkened control room in Geneva, Dr. Roussev replayed the phantom particle data for the 100th time. It still didn't obey conventional decay models. It still defied measurement. But she noticed something new. In the distribution of the particles' tunneling paths, there was a mathematical rhythm, not random, not Gaussian, but recursive. A pattern that echoed the shape of Mandelbrot fractals, self-similar, infinite in complexity. She turned to her assistant and said, "We're not watching physics, we're watching syntax." Syntax, as in language, as in code. If the matter-skew principle is real, if element zero truly contains a structural bias that favors existence over oblivion, then we are living in a universe shaped by preference that changes everything. It suggests our universe has direction, intent, and maybe, just maybe, purpose. Not in the religious sense, but in the quantum one. A universe that chooses imbalance in order to create. A cosmos that breaks symmetry not by accident, but by design. Which leads to one final question. If KX-289 carried this element to us across time, space, and entropy, what else might be waiting? What else survived the collapse of previous worlds, lingering in the corners of our physics, waiting to be found? Because if matter shouldn't exist, and yet here we are, then the universe isn't just strange, it may be deliberate. In the oldest cosmological textbooks, the death of a massive star reads like a prophecy. Fuel exhausted, gravity wins, and the star implodes in a fury of inertia. Supernova's brief, blinding scream. The corpse left behind is either a neutron star, impossibly dense, or a black hole, a cosmic abyss from which nothing escapes. That is how the universe has always told its story, until KX-289, a star that did not follow the script. As telescopes tracked the end of KX-289's life, researchers prepared for the familiar crescendo surge of neutrinos, a detonation of X-rays, the final gasp of photons lost across light years. But as the data came in, something felt wrong. The star did not explode. It did not collapse in a single flash. Instead, it hesitated, caught in a strange, recursive loop, cycling between phases of collapse and stabilization, as if locked in. A standoff with its own death. The phenomenon baffled the international network of observatories watching the event. Dr. Marissa Holt, still leading the investigation from ALMA, stared in disbelief at live data that showed the star's outer layers, pulsing, not ejecting. Inside, The calatus element Zera's mysterious crystal structure refused to break down under the crushing weight. Instead, it absorbed the force. The lattice was not shattering. It was responding, adapting, bending, and flexing like a bridge designed for impossible pressure. With each cycle, the core emitted a burst of low-frequency gravitational waves. These were not the random aftershocks of stellar death, but precise, measurable oscillations. Theorists realized that the calatus was not simply withstanding collapse, it was actively regulating it. The star's heart had become a machine, a kind of cosmic metronome, synchronizing its own slow heartbeat with the fabric of space-time itself. Some at first feared a new kind of supernova, a slow-motion disaster that might release energy on an unprecedented scale. But the energy signature never peaked. It plateaued, then oscillated, then plateaued again. The star was locked in a feedback loop where the collapse was countered, not completed. What was it becoming? A radical idea emerged, championed by Dr. Amina Sato, a quantum astrophysicist from the University of Tokyo. She proposed that KX-289 was on its way to becoming a boson star, a theoretical object composed not of neutrons or protons, but of bosons, the quantum particles that carry forces. In a boson star, matter and energy do not organize into atoms or molecules, but into a quantum field held together by its own symmetry. No boson star had ever been found until now, perhaps, but not everyone agreed. Others saw something stranger. Still, evidence of a living process at work, a cosmic evolution driven by feedback and adaptation. The calatus inside KX-289 was not passive, it was learning. Each failed collapse fed information back into the system, guiding the star toward a new equilibrium. In the words of Dr. Holt, we're not watching a death, we're witnessing an experiment. Even more shocking, the star's magnetic field changed with every pulse. Space telescopes mapping the area found that local spacetime was beginning to twist minute but measurable. Compasses on distant probes drifted as if the star's influence reached out to touch their sensors. The very rules of the neighborhood were shifting, bending around the pulsing anomaly. Some believed KX-289 was evolving into a singularity-adjacent entity, a cosmic structure that skirted the edge of a black hole without falling in, an object that defied classification, teetering between being and nothingness. But the biggest surprise was this: the star was still visible. In cosmic terms, that is a contradiction. Black holes erase their history. Neutron stars emit pulses, but only for so long. KX-289 defied both. It remained a dim, pulsing eye staring back through the void. People began to ask, was it meant to survive? Was the whole spectacle of its collapse engineered to be witnessed? The feedback loop, the preservation of visibility, the precise gravitational signals, it was as if the universe was holding up a lantern in the dark, saying, "Look here, this is not the end." For the global audience of scientists and dreamers, the experience was both exhilarating and humbling. A live stream hosted by the European Southern Observatory drew millions of viewers, many watching as the star continued its slow, impossible dance. Comments poured in. What are we witnessing? Is this a new form of life? What would you call a star that refuses to die? Maybe, in the language of cosmic myth, we could call it a star becoming dot. As the chapter closes, the greatest question hangs in the air, heavier than gravity. If a star can defy its fate and evolve beyond its script, what else is possible in a universe where even death is negotiable? In astronomy, the sky is a living record. For centuries, humans have charted the heavens with obsessive precision, mapping every flicker and shadow. A star's birth, its journey, its demisal logged in the annals of time. But when KX-289's signal lit up the cosmos, researchers made a discovery that chilled them to the core. In the oldest and newest records alike, there was no trace of this star until just decades ago. It was as if KX-289 had appeared from nowhere impossible for a giant that should be billions of years old. The search began in dusty observatory archives, faded glass plates, and digitized sky surveys. Astronomers compared star maps from every era, 19th century German star charts, Nukashis, Doizoi Tunovi, early NASA surveys from the 1960s. Nothing. Even the powerful Sloan Digital Sky Survey, which has mapped millions of celestial objects, found a blank patch where KX-289 now burned. The region wasn't empty, there was simply no sign that a hypergiant of such size had ever existed there. How does a star hide from history? Wondered Dr. Sadaf Mirza, a stellar cartographer from Karachi. It's like finding a mountain missing from every map until last week. She pored over faint traces of cosmic dust, measuring isotopic decay in the nebulae surrounding the location. The dust was ancient, older than Earth itself, yet there was no evidence of a recent supernova or stellar collision that could explain a star's sudden birth. The paradox deepened. According to its physical properties, KX-289 had to be at least 7 billion years old. Its heavy elements, the intricate lattice core, the worn shells of burned helium and carbon, these were signatures of an ancient, seasoned star, and yet all signs pointed to a cosmic trespasser, a star that did not belong to the time or place in which it now appeared. Some researchers whispered about cosmic glitches. What if space-time itself had folded, allowing a star from another epoch or region to slip into our sky? The idea was wild, but evidence began to build. A handful of anomalous readings, subtle gravitational lensing effects in the sector around KX-289 hinted that space there was subtly warped, as if the fabric of the cosmos had been pinched and stitched back together. Others proposed a more deliberate explanation, cloaking. Could some unknown force, or even an ancient civilization, have hidden KX-289 until now? It sounds like science fiction, but nature herself hides things: black holes, dark matter, particles that interact only by gravity. Why not a star, cloaked by a veil of warped space-time, revealed only when the universe was ready? This line of thinking gained traction among theorists and science communicators. Was KX-289's reappearance part of the same sequence that delivered Element Zero? Was its arrival designed, programmed, or triggered like a cosmic alarm clock, set to go off the moment humanity learned to look? Theories aside, the practical challenge was profound. Without a history, scientists could not calibrate models for KX-289's life cycle. Predictions failed. Its luminosity fluctuated with patterns unseen in other hypergiants. Its gravitational influence on nearby stars was slightly off, as if it were both present and not, exerting force through some unknown means. A new wave of AI-driven simulations was launched, attempting to reconstruct the missing past. Algorithms modeled billions of alternate histories, searching for a timeline that could produce a star like KX-289 in this specific location. None fit. Each attempt collapsed under the weight of unresolvable variables: missing mass, unexplained radiation, and above all, time itself, refusing to line up on a public webcast. Dr. Mirza asked viewers to imagine waking up to find a new continent rising in the middle of the Pacific Ocean, complete with ancient forests and fossils, yet no trace in the geologic record. Would you trust your maps, or would you question reality itself? She mused. The chat exploded with theories, time loops, alien technology, simulation glitches. The mystery gripped not only astronomers but millions of curious minds worldwide. One night, as Dr. Mirza watched the shifting light of KX-289 from her rooftop in Karachi, she wondered aloud to her team, if the universe can hide a star for billions of years, what else has it hidden from us? What else might suddenly appear, rewriting everything we thought we knew? As the world debated, one truth was clear. KX-289 was more than an astronomical anomaly. It was a challenger cosmic. Riddle sent to humble our certainty and invite us to search deeper, to wonder harder. Most scientific discoveries begin and end with matter, what it is, how it behaves, what it can build. But element zero, with its eerie phase shifting and refusal to bond, demanded new questions. Could matter reach beyond itself? Could it touch the mind? These are questions no chemistry textbook prepares you for. Yet, as the world's most advanced labs explored element zero, reality itself began to blur at the edges. It started innocently enough, at the National Institute for Materials Science. In Tsukuba, Japan, researchers exposed isolated samples of element zero captured from the stellar emissions of KX-289 to a range of electromagnetic frequencies. They hoped to unlock new properties. Instead, the sensors recorded bursts of low-frequency waves, barely distinguishable from the static of the universe. When these waves were played back on audio equipment, some described the sound as unsettling, a distant storm echoing through empty corridors. Then came the first human trials. Volunteers, screened for sensitivity and neural stability, entered the Faraday-shielded lab where element zero's wave emissions were piped through speakers. Within minutes, the subjects reported vivid, often disturbing experiences, ancestral memories, feelings of déjà vu, and, most puzzlingly, the sensation of being observed. One volunteer claimed to see flashes of faces she had never met, eyes watching her from a darkness that seemed both infinite and intimate. Researchers at first suspected suggestion, the mind's tendency to seek patterns in noise, but EEG readings told another story. Subjects exposed to element zero's frequency signature showed synchronized bursts in their temporal lobes, the seat of language, memory, and perception of time. This was not simple suggestion. The element, in some way, was communicating directly with the machinery of consciousness. Word spread quickly. Soon, a coalition of neuroscientists, physicists, and chemists formed the Element Zero Project, dedicated to exploring the frontiers of contact chemistry, the idea that the right material, in the right state, could open a channel between matter and mind. Dr. Alina Verhoeven, a cognitive scientist from Utrecht, was the first to theorize that element zero's waveforms operated not just as energy, but as a kind of information carrier. It's not broadcasting a message, she explained. It's opening a dialogue. She compared the effect to a software update, one that rewrites the code of consciousness itself. Line by line, the implications rippled across the world. Were the dreams and visions merely side effects of the brain's encounter with alien physics, or were they intentional? Was the element probing human cognition for a reason, testing, tuning, learning? In live stream sessions, scientists began inviting the public to participate remotely, playing element zero's frequency to millions. Thousands reported intense dreams, synchronicities, and shared symbol spirals. Lattice, even the geometric echo of KX-289's core. Social media filled with theories, artworks, even new philosophies born from a material that might be thinking back. A subset of researchers proposed an even wilder hypothesis. Perhaps element zero was not just a product of quantum mechanics, but a kind of interfacer, physical bridge designed to synchronize with any consciousness advanced enough to notice it. It's a universal handshake, suggested Dr. Verhoeven in an infamous TED Talk. A cosmic hello, written in the only language every intelligent being shares, matter itself. Not everyone welcomed the idea. Some called for a halt to the experiments, worried about unknown psychological risks. Was it ethical to expose human minds to a substance with such unpredictable effects? The debates echoed far beyond academia. Polls showed society split. Some saw a path to new understanding. Others feared a Pandora's box, with consequences we could not foresee. Still, the experiments continued. In a controlled trial, a group of volunteers who had never met, spread across different continents, were exposed to synchronized element zero emissions. They each described, in uncanny detail, the same dream. A corridor of light, a lattice that pulsed with color, and always the sense of a presence, waiting, just out of sight. The results made headlines around the globe. News anchors asked, was element zero a message, a test, or a trap? Could it be teaching us, or luring us into something unknown? In forums and comments sections, viewers argued and wondered. What would you do if an element spoke in your dreams? Would you answer back? At the end of one live session, Dr. Ver addressed the camera directly. We thought chemistry was about reactions and bonds. But maybe, at the edge of physics, matter is just another language one that can say, I am here. Are you ready to listen? As the world struggled to process these revelations, the nature of discovery itself seemed to shift. We were no longer just explorers, but participants entangled with a piece of the universe that refused to remain silent. If you look deeply enough into the past, into the swirling dust of our earliest myths and oldest mysteries, you find an unsettling pattern, stories of a dark star, a cosmic harbinger that appears at the end of cycles, bringing wisdom or destruction, light or shadow. Until recently, these tales were dismissed as allegory. But as the world wrestled with the revelations of KX-2-89 and element zero, those legends took on new meaning because three ancient cultures, separated by oceans and millennia, described something eerily similar to what now shimmered in our telescopes. The Olmec of ancient Mesoamerica told of a star that hid from the eyes of the world, returning only when the night was darkest, and bringing with it the knowledge of fire and time. Thousands of miles away, the Dogon people of Mali described a pale star visible only to initiates, its presence signaling the beginning of cosmic renewal, and in a lost Tibetan text, discovered in a monastery buried beneath Himalayan ice, monks chronicled the rise of a black lantern in the heavens, a sign that the wheel of worlds had turned again. It was a team of archaeoastronomers, scientists who studied the astronomical knowledge of ancient civilizations who made the connection. Dr. Paolo Mancini, poring over centuries-old star maps and carvings, was the first to spot the similarities. The location, the timing, the way each culture encoded the reappearance of a star at the edge of perception. The stories are not identical, Mancini explained, but the core pattern is unmistakable. It's as if they all saw the same thing and left a warning or a guide for those who would come after. This revelation sent a ripple through the scientific community. Had KX-289 been here before? Had it vanished and returned in cycles every few thousand years, shifting the course of civilizations each time? The possibility was breathtaking. If true, it meant that cosmic events were not just distant, impersonal catastrophes. They might be woven into the very fabric of human memory, influencing our evolution, our myths, even our sense of destiny. As word spread, teams set out across the world, revisiting archaeological sites and ancient observatories, searching for new clues. At La Venta, Mexico, a hidden chamber beneath a crumbling pyramid was unearthed. There, engraved in basalt, was a star map, one dot, offset from the rest, circled, and marked with a symbol for return. In Mali, Dogon elders recited oral histories that described the Whispering Stone, a celestial omen whose light changed those who saw it. And in Tibet, monks translated the final line of their ancient scroll, "Heed the dark lantern. When it glows, the gate stands open." What were these cultures trying to tell us? Were they warning of a danger, or inviting us to listen for a message? The sense of unease grew. Some theorists proposed that KX-289's cycles were synchronized, not to random cosmic chance, but to turning points in human history, moments of crisis or awakening. Social media lit up with speculation. Was the star a natural beacon, a cosmic clock marking the rhythm of civilizations? Or was it more, a deliberate signal, meant for anyone human or otherwise who could decode its language? Viewers everywhere were drawn into the mystery. What would you do if you found a map in stone pointing to a star that shouldn't exist? Would you try to interpret it or leave it untouched? For Dr. Mancini and his team, the search was deeply personal. In interviews, he spoke of sleepless nights, of feeling watched by the very thing he studied. "Sometimes I think the star is not just a thing in the sky," he confided, "but a memory, one that belongs to all of us, maybe to the universe itself." And as night fell over the ancient observatories and modern laboratories alike, the question remained. It is easy to imagine the periodic table as unchanging, those neat rows and columns, every square a triumph of discovery, a testament to human progress. For centuries, each new element added to its edges came with fanfare and certainty, expanding our knowledge but never threatening the order itself. Yet when the properties of element 0 from KX to 89 were finally laid bare, the world's scientists faced an unsettling truth. To accept its existence would mean tearing up the most trusted map in all of science and redrawing the boundaries of matter from the ground up. The debate began quietly in the marble halls of the International Union of Pure and Applied Chemistry, IUPAC. There, behind closed doors, chemists and physicists from every nation gathered to confront the impossible. Some argued for caution, suggesting the evidence was incomplete, an anomaly, a trick of cosmic conditions, a misinterpretation of spectral lines. But as data poured in from laboratories across 4 continents, doubts crumbled. The element was not an artifact. It was real, stable, and shockingly indifferent to our discomfort. Dr. Lia Chenghu had once called element 0 the ghost that refused to haunt, stood before her peers and described its unyielding nature, its immunity to known decade paths, its refusal to bond in ordinary chemical reactions, its unpredictable phase shifts. She showed graphs that broke the rules and spectra that couldn't be faked. Her voice, though calm, carried an undercurrent of awe. "We are no longer talking about an addition to the table," she said. "We are talking about a new language of matter." For many, this was the Copernican moment of chemistry, a revolution not of planets, but of particles, where the center no longer held. The implications went beyond academic pride. If element zero was officially recognized, entire branches of chemistry and physics would need revision. Fundamental constants might not be constant. The very laws of conservation, of energy, of mass, of information were suddenly up for debate. The discussions grew heated. Some called for a complete reclassification. Should element zero be placed in its own category, or did its presence demand a periodic table with new dimensions, one that included the possibility of matter from other universes, or forged in the impossible cores of dying stars? Would the table become a cube, a hypergraph, a living document that could flex and change as new realities emerged? A minority of dissenters, led by Dr. Ailing Foucault of Paris, voiced fears of unintended consequences. He warned, in the past, every major change in our understanding of matter has led to unpredictable outcomes: nuclear energy, quantum mechanics, genetic engineering. What if this discovery unleashes something we cannot control? His words echoed in the corridors, but progress could not be stopped. The reality was too stark. Amidst the tension, a surprising unity formed. For the first time, scientists from rival fields, and even from nations usually at odds, collaborated, openly sharing data, running joint simulations, and debating not just the nature of the element, but the very future of science itself. Social media lit up with visualizations of hypothetical new periodic tables, some swirling and infinite, others fractal and recursive. High school students, inspired by the cosmic mystery, wrote to researchers with their own sketches and theories. The story was everywhere. It became not just a scientific revolution, but a cultural one. Outside the official proceedings, the world waited. News anchors posed questions once reserved for philosophers. If the building blocks of reality can change, what does that mean for us? What else lies undiscovered, hovering just outside the margins of perception and language? Dr. Cheng, weary from weeks of debate, gave a rare public interview. "I think we must let go of certainty," she said, gazing into the camera. The table was never finished. It is a mirror for our curiosity, not a cage for our knowledge. If element zero is reland, it is then maybe the universe is asking us to keep drawing, to never stop questioning. In that moment, the periodic table, the most iconic chart in science, became a living, evolving thing. Not just a list, but a promise. A recognition that even the most fundamental truths can shift when we dare to look closer, to accept the forbidden. And as the final vote loomed, the question for every scientist and for everyone watching became simple and profound. Science is a discipline of patient observation. It requires faith that, in the endless dance of data and chance, nature will eventually reveal her secrets. But sometimes discovery leaps from the shadows, not in theory or spectrum, but in the cold, unyielding reality of something you can almost touch. For the team behind NASA's James Webb Space Telescope, that moment came unexpectedly, when a faint, metallic echo appeared in the orbit of the impossible star, KX-289. It began as a BLIPA, low contrast, anomaly in the infrared scan, something so subtle that early software routines wrote it off as noise. But Dr. Michael Yoon, a mission specialist known for his stubborn skepticism, noticed a pattern. The signal appeared at the exact same point during every orbital pass. It did not move like dust or gas. It was not a comet, nor a fragment from a past explosion. It was locked in place, a sentinel circling the dying hypergent. After weeks of argument and recalibration, Webb's full suite of instruments was brought to bear. The object came into focus, pixel by pixel, a metallic artifact, roughly 30 meters long, forged in geometric forms that defied easy explanation: half-cylinder, half-helix, surfaces patterned with recursive grooves. There was nothing natural about it. It was too regular, too purposeful. The most shocking discovery came from spectral analysis. The artifact's exterior was coated in the same forbidden substance found in KX289, element 0. Its radiation signature was unmistakably a harmonic echo, perfectly aligned with the lattice structure at the star's core. The odds of such a match by chance were infinite. This was not a rock, nor a relic, but a message, one written in a language older than stars. International excitement swelled as news broke. The world watched as agencies from NASA, ESA, and JXA scrambled to coordinate a remote probe launch, an audacious plan to approach the artifact, to image it up close, maybe even collect a fragment for study. In Mission Control, Dr. Yoon described the tension as the longest heartbeat in history. No one knew what to expect. Would the object respond? Would it activate? Or would it simply watch, silent and enigmatic, as humanity reached out? When the probe neared, it transmitted the first close-up images to Earth. The surface patterns, so crisp, so deliberately, resembled nothing known in human engineering. They were neither writing nor art, but something that hovered in between, like the blueprints of a logic beyond language. Engineers wept. Mathematicians stared in disbelief as the grooves mapped out ratios and constants, pi, the golden mean, and prime sequences, all coded into the artifact's skin. But it was the resonance that changed everything. As the probe entered the artifact's shadow, its instruments registered a surge, a low, musical pulse, synchronized perfectly with the gravitational rhythm of KX289. The object was alive in some way, not organic but responsive, as if aware of the star's strange heartbeat. For several minutes, telemetry drifted, clocks lost time, and sensors picked up a data stream no one could immediately decode, repeating intervals, recursive spirals, a chorus sung in numbers. Was this a beacon, a seed, or a lock waiting for a key no one yet possessed? Among the mission's young engineers was Aliyah Singh, a coding prodigy raised on legends of cosmic riddles. She watched the artifact's pulses and wondered if this was not an invitation, but a test. If you want to talk to an intelligence that thinks in centuries or eons, she said, you build something to last longer than memory. Maybe this is how you say hello when language itself is still being invented. As data poured in, the global conversation grew feverish. Theories bloomed. Was the artifact built by the same hand that seeded Element 0? Was it a probe, a guardian, or a message in a bottle, sent out by civilizations unimaginably distant, or even from a universe adjacent to our own? For all the speculation, one thing was clear. This object did not drift by accident. It was placed, precisely, in the orbit of a star that defied death and hid from history a cosmic conjunction that demanded explanation. As the chapter draws to a close, the probe's last image lingers on screens worldwide, the artifact gleaming in the twilight of KX289, wrapped in forbidden chemistry, whispering across the void. Deep in the heart of Illinois, where winter's chill cuts sharper than steel, the scientists at Fermilab prepared for an experiment that felt more like a séance than a calculation. They were attempting something unprecedented, to recreate the impossible. to summon element zero not from stellar collapse, but from the quiet tension of human ingenuity. Their tool was the world's most advanced quantum mirror chamber, capable of reflecting particles against themselves, creating the closest man-made equivalent to a star's final scream. The theory was simple, in a way only physicists could believe. If the right quantum symmetries were forced into a mirrored field, a fleeting echo of element zero might arise. Not the real thing, but a shadow, a glimpse of the forbidden. It was as much an act of faith as science. The last gamble of a world that had seen its certainties shattered as the experiment began. Banks of superconducting magnets hummed, bending electrons into impossible geometries. The mirrors, polished to atomic perfection, reflected the quantum dance. For a moment less than a heartbeat, sensors registered a burst of energy at frequencies matching those from KX to 89's core. In that instant, reality itself seemed to waver. Clocks lost sync. Computer screens flickered. Lab notes recorded. A doubling effect, where every measurement appeared to exist in two states at once, here and not here. Then, silence. The readings were undeniable. For a fraction of a second, element zero had manifested not synthesized in bulk, but conjured as a probabilistic apparition. And with it, something stranger still, time itself bent. The experiment's atomic clocks, accurate to a billionth of a second, reported discrepancies. Some ran ahead, others behind, as if the future and past had folded into the same breath. We saw the future blink, whispered Dr. Xinye Tan, head of quantum operations. For just a moment, every possibility overlapped. I think we touched the universe's editing room. Video logs showed more anomalies. Researchers recalled memories that didn't belong to them, flashes of lives unled. One technician described a vivid sense of being watched from the other side of the mirror by a version of himself that did not exist. The entire lab seemed to thrum with nervous electricity. It was as if, in seeking to capture the forbidden, they had become the subject of another experimenter, cosmic observer staring back. Theoretical analysis suggested that, in that moment, the laws of causality had loosened. Data emerged from the mirror chamber showing symmetrical patterns, not just in space, but in probability. The experiment had created a brief window where the constraints of cause and effect blurred Lalin. Perhaps the element to flicker into being where it did not strictly belong. For days, Fermilab's team pored over the raw data. No one could explain how element zero had formed, or why the effects were so pronounced. Some suspected an undiscovered field, a quantum substrate that element zero could borrow energy from. Others wondered if the artifact orbiting KX-289, resonating at the same forbidden frequencies, had acted as a remote catalyst, as if the universe itself was encouraging the experiment's success. It wasn't just physics that was changing. Team members reported altered dreams, déjà vu, even a subtle sense of purpose, as if touched by a whisper from the other side. Dr. Tan herself admitted to feeling watched, like we're being evaluated for how we solve a puzzle that's been waiting for us forever. The world's media, ever hungry for drama, called the mirror experiment a portal to the unknown. Philosopher-physicists debated whether the event proved the multiverse, or if it merely showed that consciousness and matter could entangle in ways still beyond our comprehension, yet barely understand. One live Q&A, if time is just a shadow, drew millions of viewers, travelers in a dream. What would you do? Flickers in a frozen sky. If you realized comment your reflection below could make decisions, because maybe, just maybe, the panel fell silent. The next great discovery, each scientist won't come privately haunted by what they'd seen, but from a mind watching this video right now, that the forbidden element was not just matter, but a kind of key. For centuries, life has been defined by what is possible by carbon chains, liquid water, and the slow alchemy of starborn elements. The boundaries of biology, we believed, were set by the rules of ordinary chemistry, but element zero shattered those rules, and with it, the imagination of every scientist who encountered it. If the universe can build an atom outside the periodic table, could it also spark a kind of life beyond anything we've known or dared to dream? In the wake of the mirror experiment, biochemists and astrobiologists joined the fray, drawn by whispers that the forbidden element didn't just alter matter, but might rewrite the very logic of existence. Dr. Felix Namier, an origin of life specialist at the Weizmann Institute, spearheaded experiments exposing basic amino acids and lipid chains, two fields resonating with element zero's signature. The results were both subtle and shocking. Molecules formed structures never seen before, organizing themselves in fractal patterns, recursive and self-repairing, as if guided by a hidden blueprint. Unlike DNA or proteins, these chains did not rely on hydrogen bonds or van der Waals forces. Instead, their stability came from a new type of resonance energy, states that flickered between probability and matter, like living shadows. Some researchers called these phenomena ghost scaffolds, structures that persisted only while element zero's frequency was present, vanishing the instant the field faded. But for those brief moments, the lab became a place of quiet awe. Electron microscopes captured shapes resembling primitive cells vesicles that flexed and divided, not by ordinary chemical triggers, but by shifting phases, as if obeying a code written in forbidden symmetry. Dr. Namier described watching these impossible cells as witnessing evolution in fast-forward, life dancing on the edge of existence. Speculation exploded. Could entire ecosystems arise under these rules of biosphere composed not of atoms and molecules, but of probabilities and patterns, forever shifting, adapting, and communicating through resonance rather than replication? If so, what would it feel like to be such a life? Would consciousness in forbidden chemistry mean flowing, flickering self-awareness, never fixed, always becoming? At a conference in Barcelona, astrobiologist Dr. Penelope Reed dared to ask, what if the universe is full of beings we simply can't detect, entities that flicker in and out of our reality, made of elements that leave no trace except in the rare moments when a dying star opens a door? The audience, a crowd of seasoned skeptics, fell silent. The question felt less like fantasy and more like a challenge. Philosophers joined the debate, pondering what life even means if the rules are so easily bent. Would such entities have memories, culture, desire? Or would they exist as pure experience cascading through possibilities as naturally as we breathe? In live streams and comment sections, viewers weighed in. If you could choose, would you want to live as a being of forbidden chemistry, eternal, shifting, forever new? Or does meaning require limits, a beginning and an end? And then came the most haunting idea of all. Dr. Namier, reviewing late-night simulation data, noticed a pattern in the ghost scaffold's resonance, a rhythm matching the Callatis's pulse, the gravitational heartbeat of KX289. It was as if the star, the element, and the lab-born forms were all tuned to the same cosmic frequency, as if the universe itself was orchestrating a symphony, inviting us to play a part. For the first time, it seemed possible that life, real thinking, evolving life could arise not just from the ordinary, but from the forbidden. And if so, then the question is, no longer can life exist elsewhere, But how many ways can the universe find to know itself? Time for stars is measured in aegis epochs, marked by the slow burning of hydrogen, the forging of heavier elements, the passage from birth to spectacular demise. But for KX289, legacy was something altogether stranger. As its impossible pulse echoed across the void, the dying star did not fade into darkness. Instead, its light lingered, a spectral anomaly looping through the centuries, refusing to obey the universe's most basic laws. In that light, humanity found not just a mystery, but a mirror. From observatories on every continent, telescopes continued to track KX289's rhythmic dimming and brightening. The star's unusual core, wrapped in the calatis of element zero, pulsed like a heartbeat frozen in time. For a moment possibly long by human standards, impossibly brief for the cosmos, KX289 became a lighthouse for anyone willing to look deeper, to question, to wonder. It was this persistence that captivated Dr. Marissa Holt, who had shepherded the discovery from its first anomalous signal. She spent night after night at the Alma Observatory, recording the star's fading light, searching for hidden patterns. Her logs became a living record, a chronicle not just of data, but of hope. "There's something about this star," she wrote, "that feels less like an ending and more like a hand reaching back through time." That hand reached far. In classrooms, Element Zero was already being taught as a challenge to the certainties of chemistry and physics. In universities, entire departments were founded to explore its effects on consciousness, life, and even philosophy. Artists, inspired by the story of the star that refused to vanish, filled galleries with works that shimmered, flickered, and changed depending on how they were viewed. The legend of KX289 began to seep into culture, a myth for a technological age, a story retold in code, in song, in questions posed around kitchen tables and late-night message boards. But its most profound legacy was uncertainty. With every answer, new questions multiplied. How many other stars were out there, bearing secrets no one had yet noticed? How many cosmic messages had gone undetected because humanity was not yet ready to see or hear them? International space agencies announced a new era of collaboration, launching missions to monitor other candidate stars whose erratic signals might hint at hidden chemistries or ancient intelligences. A global network of citizen scientists joined in, turning their backyard telescopes and spare computers into nodes of curiosity. For perhaps the first time, science felt less like an exclusive pursuit and more like a shared adventure, a collective willingness to be surprised. Yet even as research advanced, a sense of humility returned. The discovery of KX289 had not granted humanity mastery over the cosmos. If anything, it reminded us of our smallness, our place as participants, not rulers, in an ever-expanding mystery. Dr. Holt, standing on a wind-blown mountaintop, summed it up best in a rare televised address. "We have crossed a threshold. We are no longer asking just what is possible, but what is permissible. The universe is bigger, stranger, and more generous than we ever imagined." But the story was not only scientific. Around the world, those who had experienced dreams or visions during the Element Zero experiments described feeling connected not only to each other, but to something immense and benevolent. A few spoke of messages received in the hush of night, fragments of ancient languages, mathematical riddles, images of lattice and lights. Whether these were tricks of the mind or whispers from a cosmos alive with possibility, no one could say for sure. But belief grew. KX289 was not just a star, but a sign. And so, as the star's last light continued to circle back across the ages, humanity found itself at the edge of a new scientific age, one where the boundaries of knowledge were not fixed, but fluid. A world in which every certainty was an invitation, every mystery a doorway. Was the death of KX289 a warning? Or was it a gift and inheritance of awe, a legacy of questions, a cosmic promise that we are forever on the verge of something new? As the last embers of KX289's cosmic fire echoed through data streams and telescopic eyes, the world's scientific community prepared for closure. Yet, in science, every ending is just a door opening onto new strangeness. In the weeks after, the star's final pulse, a final analysis from the ALMA Observatory in Chile revealed one last, shattering twist, one that threatened to overturn not just our models of stars, but the boundaries of reality itself. Dr. Marissa Holt and her colleagues, still parsing the terabytes of raw emission data, noticed an anomaly in the isotopic ratios of element zero's remnant traces. The numbers simply didn't fit. Elemental fingerprints, usually as unique as DNA, are shaped by cosmic background radiation and the unique conditions of each stellar environment. But element zero's isotopes were alien, out of sync with every known model, incompatible with our own universe's chemical evolution. To double-check, the team compared their results with the largest database of cosmic isotopes, from nearby supernova to distant quasars. The verdict was as haunting as it was clear. Element zero had a signature that matched nothing in the known universe. It was not just extrasolar, it was extra-universal. Word of this revelation sparked a storm. International teams rushed to replicate the findings. Labs in Germany, the US, and South Africa produced the same chilling result. The forbidden element could not have formed in our universe. No matter how bizarre the conditions inside KX289, some called it a contamination, others a measurement artifact. But the numbers held. The forbidden element bore the mark of another reality, a neighboring cosmos with laws and constants all its own. The implications were dizzying. For decades, physicists had toyed with the idea of the multiverse, infinite realities, each with their own versions of space, time, and matter. Most dismissed it as beautiful speculation impossible to test, forever beyond the reach of experiment. But here, now, was a sample, however fleeting, of matter from elsewhere, delivered by a star whose life and death made sense only if it was more than just a star. Some researchers, shaken by the data, wondered if KX289 itself had been a bridger, portal or convergence point, where the edges of realities overlapped. The calatis, the phantom pulsars, the artifact in orbit, even the effect on consciousness, seemed to point toward an event far stranger than a supernova. Perhaps, Dr. Holt mused in her final field report, KX289 was not just a dying star, but a window, a point of exchange, where the universe itself traded secrets with something beyond. For the first time, the human species found itself holding a fragment of the outside. Philosophers, theologians, and dreamers weighed in, pondering what it might mean to live in a universe not unique, but one of many, a single thread in a vast cosmic tapestry. Was element zero a message, a mistake, or simply a natural process of cosmological evolution? Commentators everywhere drew new metaphors. The periodic table, once a symbol of certainty, now looked like a shoreline washed by tides. From other worlds, every law of nature, every constant, was provisional, For a new generation, the question was no longer, are we alone in the universe, but is our universe alone in reality? Amid the storm, a quiet sense of wonder rose. If KX-289 had been a meeting place, then perhaps others awaited discovery stars, or worlds where the fabric of realities ran thin, where impossible elements might drift through and change everything. Citizen scientists formed networks, scouring the sky for other anomalies, believing that somewhere another message was waiting. Dr. Holt's final log ended with a challenge. Maybe we are not just looking at a dying star. Maybe we are looking through it into something else, something that beckons us to keep going, to keep asking. As the chapter closes, the universe itself feels wider, stranger, more beautiful, and every question leads only to more doors, swinging open on the unknown. Somewhere out there, stars are dying and being born, carrying messages written in elements and echoes beyond our imagination. If you believe the universe still has secrets left to sheriff, you wonder what new voices might reach us through the darkness. Share your thoughts below. Who knows? Maybe your question will be the one that opens the next cosmic door.